Good afternoon, class. Today we're going to look at zeros of polynomials and polynomial functions.
We're continuing that discussion of functions, and I regret not putting the word function in the title. The title, it just said zeros of polynomials. I'm going to say function.
Let's make sure we're consistent with our division lingo, okay? There are several different ways of expressing algebraic division. One way, dividend divided by divisor is equal to the quotient. Remember that the quotient is the answer to a division problem. And that's probably the first way you saw division expressed, the dash and the two dots. Certainly not my favorite method of expressing division. My favorite method is just using the old fraction bar, dividend over divisor is equal to quotient. And the long division bar, if you're using a long division symbol, then the thing that's being divided, the dividend, is what goes underneath it. The thing that's doing the dividing is called the divisor. And your answer is your quotient. And with long division, as you saw briefly on that little illustration, you go through all this stuff, and the stuff you have left over, if you have anything left over, what's that called? I haven't mentioned that. When you're dividing and you have stuff left over down at the bottom, what is that stuff called down there? The remainder, yes. And synthetic division is a shortcut for polynomial long division. Let me write that down. Synthetic
So we're not going to be doing the long division today. We're going to be doing the shortcut method.
It's a shortcut for polynomial long division. But it only works when the divisor is in the form. It's a shortcut for polynomial division, polynomial long division. Polynomial division's fine, you're right. I'm going to make a note. This only works, O-N-L-Y, only works when the divisor is in the form, D-I-V-I-S-O-R, variable x plus or minus some constant, and instead of using a c for constant, we're going to use a lowercase k. The divisor must be in the form variable plus or minus a number in order for synthetic division to work.
Let me see. Look at this one.
Look at that. Could we have used could we have used synthetic division here? What's the divisor? X minus 1. So yes, you could have used polynomial long division for this problem. Synthetic division for this problem rather than that long division that they used.
The divisor's in the form x plus or minus a number.
And there's something else I need to mention. When I talk about something dividing, if the divisor divides evenly into the dividend, that means the remainder is 0. If the divisor divides evenly into the dividend, that means that the remainder is equal to 0.
For example,
2 divides evenly into 8. because 8 divided by 2 is 4 with a remainder of 0. So when I'm talking about something dividing evenly into something else, I'm just saying that the remainder is 0.
And you're just studying a formal definition for terminology they used years ago when you learned to divide numbers.
Mm-hmm. And one other thing, I think I'm going to mention the division algorithm right now rather than waiting. The division algorithm. When you learn to divide, or multiply and divide, let me ask you this. What did you learn first? Did you learn to multiply first, or did you learn to divide first? You learned to multiply first, because division is defined in terms of multiplication. When you look at a dividend divided by a divisor equals a quotient, dividend divided by divisor equals quotient. That means, what does that statement mean? That means that if you take the divisor and multiply it by the quotient, divisor times quotient, what are you going to get? If you multiply the divisor times quotient, what are you going to get? The dividend.
Mm-hmm. Why don't you write an example of it?
I'm going to write it right here. The one I said. 8 divided by 2 is equal to 4. Why does 8 divided by 2 equal 4? Because if you take the divisor 2 and multiply it by the quotient 4, what are you about to get? You're getting the dividend 8. This division algorithm is just our definition of division. What does it mean?
Stuff they've used when they were 15 divided by 3 is 5. How would you check that? 5 times 3 is 15. So you're just formally stating stuff that you've known for a long time.
Let's start with an example of synthetic division. Let's look at number 4.
Okay. Oh. I guess we haven't opened up this one yet.
Are you sure? I thought it was right there. No?
No.
Well, X that out, and
I opened it and clicked on all those just to get that done.
Number 4
is a really good first example to illustrate something.
We want to divide 3x to the 4th minus 13x cubed plus 13x squared minus 4x plus 3 by x minus 3. Let me make sure I didn't miscopy this. 3x to the 4th minus 13x cubed plus 10x squared.
No, 13x
plus
squared.
13x squared minus 4x plus 3. Yeah, that's it.
So you're just going to illustrate. Synthetic division is not one of those things that you can easily write out a recipe for. It's not the cut point method.
The first thing we're going to do is determine our constant k. Our constant k, well, you have to add, the first thing we're going to do is make sure we can use synthetic division. Look at the divisor. Is that in the desired form? You can't have a leading coefficient other than 1. Remember we said that for synthetic division to work, the divisor must be in the form variable plus or minus a number k. Do we have that? Yes, so we determine the k value. The k value is exactly the opposite of the number you see there. The k value is the number that makes the divisor equal 0. What number would make that divisor equal 0? It's not negative 3. What would you have to plug in for x to get a divisor of 0? 3. It's the opposite of what you see. So your k value is equal to positive 3. You'll notice I skipped a line.
But you're going to use
And now,
3 lines on lined paper. This takes 3 lines.
I'm going to write some column headings. I'll start with the largest variable in the dividend, x to the 4th, and then I have to have a column for every power of x after that. Even if one had been omitted, we'd have to have a column for that. So you have an x to the 4th, you need an x cubed, an x squared, an x, and finally a constant c.
When I said 3 lines, I guess I wasn't counting the column headings.
Yeah, that's 3 lines.
No.
Oh, you mean to get the answer? Oh, okay. No, you weren't. Now we'll write the coefficients for each term. The coefficient of x to the 4th is positive 3. The coefficient for x cubed is a negative 13. For x squared, it's a positive 13. For x, the coefficient is a negative 4. My constant is a positive 3. Then we're going to skip a line.
So this is how I was getting 3, not counting the column heading.
Well, you didn't used to put column headings. I was the one that always put those column headings.
1, 2, 3, 4 lines.
Unless you have large award-winning penmanship like me, in which case then I may burst into larger writing just to show off how fancy I can write. Here's what you do. The first thing to start this process, you take the leading coefficient, whatever it is, you bring that down. We'll discuss why we do that in a moment. Then you take this constant that you have, you're going to multiply by that each time after you bring a number down, as long as you have columns. 3 times 3 gives us a positive 9. Negative 13 plus 9 gives us a negative 4. Then we start all over. Negative 4 times 3, that's a negative 12. 13 minus 12 gives me a positive 1. You'll see why I'm putting that plus sign there in a moment. Then we take the positive 1 times 3. That gives us a positive 3. Negative 4 plus 3 gives us another positive 1.
No, negative 1.
Negative 1, thank you. A negative 1.
Let's see if they can
3 times negative 1 will give me what? Negative 3. 3 minus 3, what's that last number we have here? 0. The last number will correspond to your remainder. The remainder is 0. That means x minus 3 divided evenly into that large dividend. This last number will be the remainder. Remainder is 0 means that x minus 3 divided in evenly. Think about what we had. You had a 3x to the 4th to start with, and you divided it by an x to the 1st power. We had a 3x to the 4th, and you divided it by an x to the 1st power. What is that going to give you? You get, there's only one thing you can cancel above and below. What is it? To reduce that fraction. You can cancel an x above and below. So cancel the x. Cancel an x. That means we have how many factors of x? 3. That's why that leading 3 is coming down as the leading 3 in your quotient. Your power will be 1 less than what you started with, because you're always going to have just an x to the 1st power there. Dividing that term, that leading term, by x to the 1st power, you have 3x cubed. So your leading power in your quotient is x cubed. Then you just sweep across, decreasing by 1. Minus 4x squared plus 1x minus 1. We have x cubed, x squared, x to the first power, finally no x. Here's my quotient. I guess I'll write it all out. The quotient is 3x cubed minus 4x squared plus 1x minus 1.
And if it asks for the remainder, you'd say R equals...
Or they may want plus remainder over dividends. Divisors. So.
Not when it's a 0.
Not when it's a 0, though.
R equals 0.
If they had a little spot for you to type in the remainder, you would type a 0 for this one. Any questions there?
So you write down the coefficients.
You determine the k value first. Then you write your column headings based on the powers in the dividend. Then you write down the coefficients. You skip a line, and you begin that repetitive multiply, put the number down. There, bring down, multiply, combine, multiply, combine, and you continue doing that until you're out of columns. Look at your looking back at number 4.
Let me type in that answer.
3x cubed.
X.
Have we typed exponents before?
Yeah, we typed
yes.
exponents before.
Okay. Notice
I'm looking at the wrong page. So minus 4
x squared
arrow minus 4x squared arrow
plus x minus 1. Let's do another synthetic division problem. Let's look at number 1.
Oh, look at that. Multiple choice.
And those are B's instead of... look how they're denoting the remainder in those multiple choice problems. That's right.
So we're not seeing them.
B cubed minus 5b squared plus 18b minus 13 all divided by b minus 3. Well, this is lousy. It's the same k value, isn't it?
Oh.
Well, the k value won't stay the same number. I'm going to make sure I didn't miscopy it. Okay. Can we apply synthetic division? Look at the divisor. Variable plus or minus a number. Can we use that? Yes. What's my k value? Not negative. It's exactly the opposite of what you see. If we had more time to go into this theory of equations, we would be saying that the k value must make the divisor be a 0 for the divisor. Yeah, but just change the sign on the number you see there. The k value is another positive 3, and that is just a coincidence that it's a positive 3. And then we put in our column headings. What's our largest power appearing in the dividend? Okay, so we have a b cubed, a b squared, a b to the first power, and finally our constant. We fill in the coefficients across the top. What's the coefficient of b cubed? 1, I agree.
Yes.
I don't see anything, so it's a 1 for b cubed. For b squared? -5, I agree. B? 18. And finally, my constant? -13. Then we skip a line, skip a row, and draw a line. What's the leading coefficient of my quotient? What do I write here to get started with? 1. It's that number, the leading coefficient, that's what you carry down, okay? Seems like it's unfortunate there's so many 3's popping up with number 4 and then this one. But whatever that leading coefficient is, bring it down. And if you stop and think, why is that the case? You have a b cubed divided by a b to the first power. A b cubed divided by a b to the first power, you cancel a b above and below, and that gives you what? A 1b squared. This letter down here in the divisor, whatever that letter, that leading coefficient there in the divisor is always going to be a 1. And so whatever number's there, that's what you bring down.
And that's what this is an arrow. Okay? Trying to show you carry that down, and I added it right here. I carried that 3 down. Carry down the first number.
3 times 1 is a positive 3. Negative 5 plus 3 gives me a negative 2. What do I do next? You take the negative 2 times 3. That gives you a negative 6. And then? Okay, 18 minus 6 gives me a positive 12. Next? 12 times 3 gives us a positive 36.
Ooh.
Am I going to have a remainder of 0 here? No. Negative 13 plus 36, is that a positive 24? No, 23, isn't it? Positive 23. That positive 23, that last number, is the remainder. Did b minus 3 divide in evenly into the dividend? No, because we have a remainder of positive 23. Let's figure out the variable parts. We started with the b cubed. We divided it by b. So what's the variable part to this leading term? B squared, then b to the first power, and finally no b. So we have a 1b squared minus 2b plus 12, and our remainder was positive 23.
This is one that's multiple choice, so let's look at those choices.
A, B, C, or D. I bet you we can pick it out just based on the remainder. C, I agree. B squared minus 12b plus 12 with a remainder of 23. B squared minus 2b. Any questions there?
Do they have the pattern for this synthetic division? It does follow a repetitive pattern.
There's something called the remainder theorem that I want to mention because it is specifically listed as a student learning outcome by the state of Texas for this course. Let's see, do I have room down here? I just want to look at an example. Suppose we had, I want to use this dividend, but I don't like those variables of b. Since I'm making up the example, I'm going to call this thing p of x, a polynomial function. Instead of b's, I'm going to use x cubed. X cubed minus 5x squared plus 18x minus 13. Here's my function. It's the same as what we had up here, except I just changed the b to an x. Suppose I wanted to find p of 5. Y'all know how function notation, not 5, p of 3. Y'all know how function notation works.
You're using a p instead of an f just to stand for
polynomial, but which is standard when working with zeros of polynomial functions. They use p's a lot rather than f's, but it's the same thing. P of 3. We know how function notation works. That means go to the function p, and wherever you see an x, replace it with 3. So here goes. We'll have a 3 cubed minus a 5 times a 3 squared plus an 18 times a 3 minus 13. We're plugging in a 3 everywhere there's an x. And look at Tony's calculator up here. He's punching this in for us. 3 cubed minus 5 times 3 squared.
I'm putting it in parentheses just to make it look like what you wrote.
Plus 18 times 3 minus 13. Anyone want to guess? What are we going to get when we do this? Well, okay, let's look and see what it is. There it is. Look at that. We got 23. Wait a minute. We just saw that number 23 a moment ago. Where do we see 23? The remainder. If you use synthetic division with a k-value, the way we did right here, whatever you get as the remainder is the value of the function at that k-value. That's called the remainder theorem. And you say, well, why on earth? Back in the olden days, this was very significant. If you looked in real old algebra books before modern calculators, they would use... Yeah, before calculators, you'd be going along and then just all of a sudden, randomly, as you're reading examples, you'd see them with a little synthetic division tableau. Why? Because they need to evaluate functions. Suppose we had wanted to use, instead of a 3, we had wanted to use something like a 14. To plug in 14 here and here. 14 cubed. Remember, you didn't have a calculator. If they didn't have a calculator, it was a lot easier using synthetic division to get the value of the function at the given number. Because with synthetic division, is there any exponentiation? Do you wind up with some big number being cubed? No. That's why the remainder theorem used to be so significant, because it allowed you to evaluate functions that have high exponents, but you don't have to perform any of the exponentiation.
And then with calculators, it just became so unused. Del Mar College was one of them. Colleges and universities across the nation stopped doing that. And then about 10 years ago?
With Project PSLO, where the state legislature...
State of Texas gave everyone a surprise. They started listing everything we've got to teach. Before then, algebra, the school could decide what to teach. Fine. And if you're a private school, I guess you can still do that, but we're not. We get tax dollars. We're a community college, so we've got to do what the state tells us, and that was the thing that shocked everyone.
Wait a minute.
We got to start back teaching that.
We have to start back teaching the remainder theorem. With calculators, it isn't really important, but if you have to understand who was deciding on these student learning outcomes. The people that were deciding it may not have math degrees. They were sitting around. I like to think of it as smoke-filled rooms, everyone got their cigarettes and it's all smoky. What do our students need to know from algebra?
And they're looking at
some good old boy saw something saying the remainder theorem, and he was like, yeah, the remainder theorem, they got to know how to divide. Well, this is way more than division, okay? But I think that in all likelihood, they didn't really know what the remainder theorem was, and they thought exactly that. Oh, yeah, remainders, they got to know how to divide. We need to include that. And that's how we got included, the remainder theorem. And here's the funny thing. There's something called the fundamental theorem of algebra. The fundamental theorem of algebra, that sounds pretty important. Right?
They didn't list
They didn't state that we have to teach the fundamental theorem of algebra in any of our algebra classes. That's not listed. I'm going to tell y'all what it is in a moment, but they never listed that by name. The fundamental theorem of algebra, it is important, but it wasn't listed. The remainder theorem was listed. So, here we go. Let's look at number 5. Number 5. Use the remainder theorem in synthetic division to find f of k for the given value of k. They give you the k value. Now, before this, if we'd been doing, they could have given this problem to us back when we were looking at function notation. They give us the function f of x. Let me write this down.
What is that sound?
It's my little microphone. I have it lower than normally. Yeah. Okay. We have a negative 1x cubed minus 6x squared minus 8x plus 2, and they give us a k-value of negative 4. They want us to find f of negative 4.
We know that means plug it in. But they want us to use synthetic division instead of plugging it in.
Well, they tell us the k-value, so we're not changing the sign. Realize on the previous problem, they weren't giving us the k-value. We had to find the k-value, and I said the k-value is exactly the opposite of what you see. Now, we don't need to know the divisor, but here the divisor was x minus 3. The k-value became a positive 3. When you're going backwards, when they give you the k-value, notice the divisor, it's the variable, and exactly the opposite of what you see. So if we had needed to know the divisor, and in this problem we don't, but in a moment we will, it would be x and a plus 4. The k-value is exactly the opposite of the constant in your divisor. But here we go. We have a k-value of negative 4. I'm just rambling. We should already be through with this problem. That's one of the problems with this. When it comes to zeros of polynomials, I could just ramble on about this.
That all day.
I could certainly use 2 weeks of classes. We have an x cubed, an x squared, an x, and a constant. Call out the numbers I have across here. Call out the leading coefficients. We'll start here. Negative 1, I agree. Here. Negative 6. Here. Negative 8. And? Okay. Then we skip a line. And what do we do next? Bring down the negative 1 times negative 4 gives me a positive 4. Negative 6 plus 4 gives me a negative 2. What do we do with the negative 2? Times negative 4, that gives me a positive 8. Here. Negative 8 plus 8 gives me a 0. What are we going to put here? 0 times negative 4 gives me another 0. I guess I put a plus there just because it looks better, although it doesn't matter. And what have we got here? A positive 2. What's the value of f of negative 4? Remember, this was the good one to look at. If we plugged in 3, we got what? 23. So if we plug in negative 4, what are we going to get? That remainder right there, positive 2. F of negative 4 is equal to positive 2.
Do y'all agree that there was no real big numbers in any of this work here? You could do it pretty much without a calculator. Now, stop for a moment and ask yourself, how easy would it be to plug negative 4 in for x without a calculator? You'd have to cube it. Negative 4 times negative 4 is negative 16. Positive 16 times a negative 4 is a negative 64. We have a minus negative, so that's a positive 64.
Then in the next one, you plugged in that negative 4 squared. That's 16 times a negative 6.
You'll notice I'm not using a calculator because I'm trying to talk about what you would do before calculators. Okay? So 16 times 6 is 96. So we have, I forgot, what was it, 64?
Oh, it doesn't matter.
Minus 96.
Why don't you punch it into the calculator just to show them that we're not making this stuff up?
Well, really... they saw it with 23, and they're about to see that it's true.
Oh, yeah,
I'm about to
punch it in.
And get the right answer. What's the number?
2. Now, on the test, if the problem says use the synthetic division, use the remainder theorem, and you just plug in, that's fine. That's fine. That's not something that's, it's something archaic. I guess like quilting. I guess quilting is archaic. Does anyone quilt here? No?
You know what that means? You make these blanket things, not blankets, they're called quilts.
Yeah.
When we were young, old people made quilts. And now, all those old people...
We went to a county fair to buy a handmade quilt because when we were there the last time in 1984, there was a whole room full of quilts, okay? Who would imagine 41 years later,
there wasn't a single quilt.
And the people there seemed to think we were...
Insane.
You've come to buy quilts because there was... Well, we don't have a quilting contest anymore.
Well, you did in 1984.
I could tell they were sort of scared.
I thought those people are insane.
They drove 350 miles to go to a fair to buy a quilt.
Based on the fact that they had quilts for sale 41 years ago. Wow.
Now, we should have factored in the fact that young people didn't learn how to quilt. Gen X did not learn how to quilt, so there are no more quilts.
I don't think baby boomers learned to quilt. Well, baby boomers should be quilting and there'd be quilts.
Oh, wow, you're right.
I know. Baby boomers quit the quilting. You just go buy.
What came before baby boomers?
Oh, I don't know.
Okay, we're getting distracted, Tony. We have to be through by 4.
Well, good luck with that.
Okay. We need to start. I need to talk some, okay?
But at this point, we've factored stuff with x squares in it. You know, where you draw the 2 parentheses. We have not factored anything with the x to the 3rd until today. What we're about to learn now is how to factor something that has an x cubed, not just an x squared. If I could cover this up, which I can't, we've been factoring stuff like 8x squared minus 15x plus 4. But we've never factored anything like that has a 3x cubed in front of the quadratic. So go ahead and start talking to me.
Okay, I have some definitions first. The number k is a 0. I'm defining the word 0. It's also called root, but I guess that's not quilting. People don't do that anymore.
Because it sounds like a square root.
I know. I agree. Okay, I agree. K is a 0 of the polynomial function p of x means p of k is equal to 0. If you take that k value and plug it into the function, you get a 0. Or, when you use synthetic division, the remainder is equal to 0. So, or remainder. That's the result of that remainder theorem.
Like this k on number 5.
Is negative 4 a 0 of f of x? If you plug in negative 4, do you get a 0? If you plug in negative 4, what do you get? A 2. So, no, negative 4 is not a 0. Let's look back at number 1. Let's see. Is 3 a 0 of this function on top? Yes, because if you plug in 3 into the top, you get 0. So 3 is a 0 on number 4, but on number 5, negative 4 is not a 0.
What about this red 3 on number 1?
Would that red 3 be a 0? No, because if you plug in that red 3, you're going to get a 23. Okay. And occasionally I do still accidentally mentioned used the terminology root. But as Tony said, most books have done away with that because it does, when you say roots in a math environment, people start thinking square roots and cube roots, and that's not what we have. That's not the same thing. We have something called the factor theorem. The factor theorem says that K is a zero of P of X if and only if X minus K is a factor. If K is a zero, that means that X minus K, when you divide by X minus K, I should say, the remainder is 0. Therefore, X minus K divides evenly into the dividend, giving us X minus K being a factor.
Number 4 illustrates that really nicely. You would ask them, does it divide evenly?
X minus 3, does it divide evenly into that? Yes, it does. So 3 is a 0. And X minus 3 is a factor. X minus 3 divided evenly into that dividend. And recall the division algorithm. The division algorithm, once again, we said that, where is it? Okay. Remember the division algorithm. The divisor times the quotient will give you back that dividend. And we're going to use that in order to factor higher order polynomials. Our goal is to factor higher order polynomials,
stuff with an x cubed in it, rather than just an x squared.
An x cubed or an x to the 4th, what have you. Our goal is to factor higher order polynomials by using synthetic division and the division algorithm until you get something that can be factored by trial and error. You're going to break down the polynomial using synthetic division and the division algorithm until you get something that you can factor by trial and error. So use synthetic division and the division algorithm until
you get a quadratic. Which you can factor with trial and error.
And I'll make a little parenthetical note of that. The quadratic, you'll be able to factor that by trial and error. The way we were doing the second week of the semester.
Just going to go ahead and show the example.
Yeah, let's do it.
Okay, I think we're talking and talking and talking. You just need to see an example. It's not as bad as it sounds.
I don't think it sounded bad.
I think it sounds pretty bad.
Okay, number 6. Let's go back to that number 6. And hopefully y'all agree that we have not factored anything with an x cubed so far.
All we factored is x squares. Who can answer this for me? When we have an x square and we're factoring a quadratic, how many sets of parentheses do you have? When you're factoring with trial and error, how many sets of parentheses does your answer have?
2. With the x cube, how many sets of parentheses do you expect your answer to have? 3.
Yes, that's a
If it were next to the 4th, how many sets of parentheses would you expect to have?
4.
That's hinting at the fundamental theorem of algebra. The fundamental theorem of algebra says that the number of zeros, hence the number of factors, cannot exceed the biggest exponent.
It's almost always equal to it.
Maybe you could wind up with just two sets of parentheses if you had x minus 5, x minus 5, if you had repeated factors, okay? But if you wrote it without exponents, you're factoring something with an x cubed, you should expect 3 sets of parentheses. Factoring something with an x to the 4th, you should expect 4 sets of parentheses, and so on. They gave us
if you were trying to factor what I have here, 8x squared minus 15x plus 4, you'd write your 2 sets of parentheses. Now there's an x cubed, 3 sets of parentheses.
But you're not going to write them all out at once yet. They give us something else. I'm not through writing the problem down. They tell us that they want us to factor f of x into linear factors. That means no exponents, just x's. You can't have an x squared in your final answer. And they tell us that k is a 0 of f of x. K is equal to positive 1. K equals positive 1 is a 0. We're going to factor, we want to factor f of x. We're expecting 3 sets of parentheses in our final answer.
So you're going to show them how to get those 3 sets of parentheses.
The first set of parentheses that I come up with is the factor associated with the k value. Be careful. I have my x. What factor is the result of that k value? Look back over here. Remember what we were saying. If k is negative 4, the divisor, hence the factor, would be x plus 4, but it doesn't divide it evenly, so it isn't a factor, okay? But what you see, the k value and the constant in the divisor are exactly the opposite. The k value is 3. You were dividing by x minus 3. Same thing here. There's too many 3's, I guess. With that in mind,
generated before we started. But
what factor are we going to get as a result of that k value? Remember, the factor theorem says if k is a 0, x minus k is the factor. That sign you see there is the opposite of what you see for the 0. So with that in mind, I'm waiting. We have x minus 1, correct. The k value is a positive 1, so the factor has a minus 1 on it. Let's use synthetic division now. You know what? I'm going to move it down a little bit. K equals 1.
Oh, wow, your beautiful k looks...
And then we have an x cubed, x squared, x, and constant. Let's fill in the coefficients. Call them out going across. Here,
3,
here,
8,
here,
negative 15,
and here.
4.
And then we skip a line. So,
hey, I wonder if anyone can tell me what the remainder is going to be on this. Keep in mind it says k equals 1 is a 0. So
what will the
remainder
be?
To be?
0. That's right. So let's get started. We bring down the 3 and then 3 times 1 gives me a positive 3. 8 plus 3 gives me
11,
times
1,
still gives me a positive 11. Negative 15 plus 11. Negative 4 times 1 gives me a, and a remainder of, and we knew we were going to get a 0 because they told us that 1 was a 0. That means that the remainder has to be 0. So we now have our quotient. The divisor is x minus 1. The quotient, we have a 3. What's the variable part? X squared, then x, and then no x.
I think
So
right now,
using-
wait, before writing any more, I think just say, to fill these other two sets of parentheses,
Here's the thing you got to factor. Now we need to factor 3x squared plus 11x minus 4.
now is that something we factored this semester? Something like that. Yeah, it has an x squared in it.
Divide our two sets of parentheses. 3x squared. Well, that's pretty nice. There's only one pair, really, that could give us a 3. 1 times 3, so 1x times 3x. Oh, what do we know about our signs?
They're both going to be negative.
Oh.
Positive
A positive and a negative. I was just thinking,
been a
why
while since
couldn't
we've done
this?
this.
I was looking at this thinking, why couldn't that be a plus? But the last sign's a minus. That means we're going to have one plus and one minus. We'll wait to figure out which one in a moment. And then, what times what will give us 4? We can have a 1 times 4 or 2 times 2. I can play it out in my head, and I don't see a 2 times 2 doing it. Here's one of these things that I like, one of these little tricks I use that works sometime. If you multiplied 3 times 4, you'd get 12. If that middle term is just 1 away from that product, you should try the 1 and the 4. You can try the 2 and 2. You'll see you're not going to get it, okay? I think we need the 1 and the 4. I'm going to put the 4 here and the 1 there. What's my outer product then? We'll worry about the signs in a moment. What's my outer product? Okay, so that's a positive 1x. What's my inner product? Really?
You don't know the
I don't know that's going to become positive. You're right. That's just a 1x. What's the inner product? 12x. We need to subtract these things in a way to get a positive 12. A positive 11. So that would mean a positive 12 and a negative 1.
How should we arrange this?
So how do we arrange the signs? You want to get a positive 12x to get back that positive 11x. What sign should I put here to give us a product? The inner product be a positive 12x. A plus, and there's the minus.
Here's your other two sets of parentheses.
X plus 4 and 3x minus 1. This is really amazing. If you FOILed out x minus 1 times x plus 4, combine your like terms, then took 3x minus 1, distributed the 3x over all of them, distributed the minus 1 all over all the terms, and then combined like terms, you would get back the dividend 3x cubed plus 8x squared minus 15x plus 4. If you FOILed this out and then distributed and combined like terms, you'd get back that function f of x. The first factor that I write down, although multiplication is commutative, you could write 3x minus 1 times x minus 1 times x plus 4. I put the factor that comes from the k value first, and then the other two. But it doesn't matter the order in which you type them in. Let's type these in, the answers,
we might have already been timed out.
Yeah, if we haven't, let's type it in. Parentheses, x minus 1, right parenthesis, left parenthesis, x plus 4, right parenthesis, and 3x minus 1. And once again, the order in which we wrote those parentheses isn't significant. You could have put, as long as you have the same thing inside all three sets of parentheses, you could have put the 3x minus 1 first when you were typing it in.
Notice, if you go first term times first term times first term, you get 3x cubed. X times 3x, 3x cubed.
No.
X times 3x is 3x cubed.
That's right.
Oh, you said no.
Oh.
Then negative
Yeah.
1 times 4 times negative 4. If you multiply the last terms, you get the last number, positive 4. Okay? Right.
Now, before we go on, switch back. We know 1 0 here. They could have asked us to find the remaining zeros. The fundamental theorem of algebra says that the number of zeros cannot be more than that biggest exponent. We already know, we know 1 0. When is x minus 1 equal to 0? It's equal to 0 when we have x minus 1 times x plus 4 times 3x minus 1. And we want to know, when is that equal to 0? Well, the first one is when x equals 1. Well, we already knew that was a 0. They gave us that was a 0. Give me another 0. When is x plus 4 equal to 0? When x equals negative 4. There's the second 0. There's one more. What's the third remaining 0? What would I do? I'd take the 3x minus 1, set it equal to 0. What are we going to get? A positive 1/3. So we now have a way of solving higher, or not only factoring higher order polynomials, but we can also set those things equal to 0 and solve them. And the number of unique solutions cannot exceed the largest exponent. Any questions there?
So
This is a lot to absorb, I know.
number 7 is the same type of problem we're about to do. You start off, get the first factor by changing the sign on the 0.
Apply synthetic division to break down the polynomial so that it's quadratic. Then you have to remember how to factor a quadratic by trial and error, and those two factors you pick up give you the last two factors in your answer.
Let's do number 7. Oh,
And now, don't answer this for them, Tony, but I want them to be thinking. There's a drawback. There is a drawback to this method. It's great, okay, here's the 0. Use that 0 to break it down so that you can get something you can factor by trial and error. But there is one big drawback. What is that drawback?
they've got to give you something.
What must you know? And if they don't give it to you, you've got to find one.
That first
You have to know that the 0, in other words, the divisor, okay? You have to know a number that can be plugged in to make the function equal 0. That's the problem.
But it's amazingly simple to find, and we'll do that in the last problems. It's the fact that it doesn't just say factor.
It gives you the
Gotta
0.
give you that
You
0.
have to have a 0 in order to use this method. And if you don't know a 0, suppose they had it, switch over to my paper. Suppose they hadn't told us that k equals 5 was a 0. Suppose they hadn't told us that. What number would we use? What number would we use for k then?
Well, we're going to show them how to find those numbers in a moment.
Okay, but hopefully you see that's the drawback to this method. And it's not that bad.
Also,
Okay, I look and see.
They didn't say k equals negative 5. It just says negative 5. But you need to go ahead and label it k equals.
Okay, how many sets of parentheses do I expect to have in the factorization? 3. I'll write them down. 1, 2, 3. What's the factor that's resulting from the 0 of negative 5? The variable is x plus 5. That's right. Remember, whatever that 0 is, when you plug it into that factor, it has to give you 0. So that's why this constant has to be exactly the opposite of the 0. Because what would you have there? What do you need there? So when you plug in a negative 5, you get 0. Well, you need a positive 5. Now we're ready to set up our synthetic division tableau. We have a k value equal to negative 5. Goodness, let me try moving this some more. We have an x cubed, x squared, x, and finally a constant. What am I going to write across right here? 2, 5, negative 23, the coefficient of x, and 10. I agree. Then what do we do? Skip a line. Skip a line and draw a line. And then bring 2 down. 2 times gives me, okay, 5 minus 10 gives me
positive or negative?
Negative 5 times negative 5 gives me a positive 25. Negative 23 plus 25 gives me a positive 2. What am I going to have here? Negative 10. And what are we about to get as our remainder? 0. And we knew that that was going to be 0 because they told us that negative 5 is a 0.
They didn't label it k equals, but you knew to do that.
And then variable part in our quotient. 2 x squared, then the x and the constant. Here's the quadratic we have to factor. We now need to factor 2x squared minus 5x plus 2. I'll write my 2 sets of parentheses. I like the signs here. What are the signs going to be inside these parentheses? The last sign's a plus, so you'll have not 2 pluses. 2 might, remember, if the last sign is plus, you have 2 of the first sign. So 2 minuses. Any questions there? Remember, if the last sign's a minus, that's when you have 1 of each. If the last sign is a plus, you have 2 of the first sign. So minus and minus. 2x squared. What times what's going to give us 2?
Not a lot of numbers.
I think there's only one pair. 1 times 2, so 1x times 2x. Oh, I really like this problem. And then 2. What's that going to give us? I mean, there's only one possibility. 2 times 1, 1 times 2, however you want to think about it.
How should you arrange them?
How should you arrange it? Should I put the 1 in the first and the 2 in the second, or vice versa? Vice versa. You can't put the 2 there. If you put the 2 here, if you put the 2 there, then both of those numbers are divisible by 2. You can't have a common factor. So other than 1, that's right. So we better put the 2 there, the 1 there. Let's check. What's my outer product? Here I am checking. X times a negative 1 gives me negative 1x, okay. Negative 2 times 2x gives me a negative 4x. Negative 1 minus 4 gives me a... Is that what we needed? Yes, it is. So, we've got the factorization complete. We had an x plus 5. We also have an x minus 2 and a 2x minus 1. There's the factorization.
So with the instructions, that student years ago when he said his teacher was an idiot because he told him to study the instructions, and I thought, oh wow, that's a good idea. I got to tell the students that. If the instructions say factor into linear factors, what do? Go x minus k to get one ordered pair, synthetic division, factor the quotient. Okay.
Hey, suppose they asked for the zeros. What are the zeros of f of x? Well, when is x plus 5? When is x plus 5 equal to 0? When x is negative 5, okay. What's another one? Okay, when is x minus 2 equal to 0? Move the 2 over, that gives you a positive 2. And 1/2, bring the 1 over, the negative 1 becomes a positive 1 divided by 2. There they are. Hey, is it possible there's more zeros that we just haven't found? No, the fundamental theorem of algebra says you cannot have more zeros than the largest exponent in the function.
You might hear zeros also called solutions to polynomial equations.
Yeah. Mm-hmm. What else?
Let's do number 8. It's the same type of problem. Oh, wait, no. I haven't even typed in this answer. Let me see. X
plus 5,
close parentheses.
X minus 2,
close parentheses, and
2x minus 1.
Now we'll go on to the next one.
Number 8.
Same instructions, just bigger numbers.
The thing we're trying to factor is f of x equals 3x cubed plus 7x squared minus 155x. Is that a 225 plus 225? And they tell us that negative 9, I'll write it as k equals negative 9 is a 0. 3, 7, negative 155, and positive 225. Okay. And I like writing those 3 sets of parentheses right on. Do we normally do that? I don't know that we do. No. Oh, by the way, x cubed, so that means there should be 3 linear factors.
And the reason it says linear is there's no exponents in any of the sets of parentheses. That's why it says linear. Linear means no exponents.
You're not going to have x squares, just x's inside the factors. Those are the most desirable type of polynomials, the kind that can be factored into linear factors. Okay, what's my first factor?
X plus 9.
Okay, it's exactly the opposite of that k value. So an x and a plus 9. Now we'll make our little simplex tableau. K equals
synthetic division.
Synthetic division. Where did I get simplex from? Wrong course. Synthetic division. I think it's the S's that are messing me up. X cubed, x squared, x and a constant. Now, this hasn't happened, but suppose there hadn't been an x term. We have a 3 for x cubed, And whatever the largest power is, you can't skip powers. You have to go, once you start at x cubed, you have to have x squared, x, and a constant. And so that would be a 7. Suppose it skipped this x term. If one term is missing, then what's the coefficient? You have to put a number there. 0.
But
If there were a term missing, you put a 0. Fortunately, there isn't one missing, but if there were, then I draw my line. And what do I do to get started? Bring down the 3 times gives me a negative 27. So 7 minus 27 gives me a negative 20. Here, what am I going to put underneath that negative 155?
Plus 180.
Okay, negative 9 times negative 20. I agree with that, plus 180. Negative 55, negative 155 plus 180. Is that giving me a positive 25? Times negative 9. I know what I'm going to get here. What am I going to get down here? Oh, that's a negative, you're right, that's a negative 225, and I wasn't even doing the multiplication because I knew I needed a 0 here, so that number had to work out to be a negative 225, but okay, yeah, negative 9 times 25, that wasn't too hard.
going back to that remainder theorem, can you imagine before calculators if someone needed to plug that negative 9 in for x?
I assure
Negative
you,
9
if
times
you had
negative
to
9
do
times-
this synthetic division stuff would be a lot quicker and easier than just plugging in the negative 9 by hand and going through all of that. Because with synthetic division, all you're doing is multiplying and adding or subtracting. There's none of this negative 9 times negative 9 times negative 9. So the remainder theorem, it used to be extremely important. It's like home telephones. Those used to be extremely important.
Mm-hmm.
Now I don't know of anyone that has one, but okay, I'm writing the variable part here. X squared and then an x. So we now need to factor. What have we got to factor? What are we going to factor now? 3x squared minus 20x plus 25.
They might just want
I
to draw
agree.
2 parentheses underneath that 3x squared plus 25, but you're writing out what they're doing.
Right. Oh, I like the signs. What do I know about the signs in the parentheses? Okay, the last sign's a plus, so you have 2 of those first signs. So I can write those down. 3x squared. 1
Yeah.
times 3. So these are pretty, even though the numbers are generated randomly, they're algorithmically generated also. They're not going to give you anything really awful. You're not going to wind up with a 28x squared. Well, what do I use? 1 times 28, 2 times 4, 2 times 12, 2 times 14, or 4 times 7. So notice they're giving you, they're rigged to work out pretty nicely. What about 25? There's only 2 possibilities. 1 times 25 or 5 times 5. Which one do you want to try?
5 times 5.
I think 5 times
You want
5
to
is
try
going
5
to do
times
it.
5 because you know that's the one that works.
Okay. And if you check the outer product, x times a negative 5 is a negative 5x. Negative 5 times a 3x is a negative 15x. Negative 5 minus 15 is a negative 20x. Is that what we needed? Yes, it is. So, my other 2 factors are x minus 5 and 3x minus 5.
Okay.
Any questions there?
Type that in. X plus 9 is the first setup.
Oh, and the most common mistake is people will type in those last two factors. They won't type in the easy factor, the one that comes from the k value.
Yeah.
So that's why I want to write that first so you don't forget there is a third factor. And it comes from that k value, the 0. If you're right, if you're factoring something with the x cubed into linear factors, you must have 3 sets of parentheses.
And then what is it? X minus 5 and 3x
Minus 5.
Now, really,
Realize
it doesn't matter the order, but I always like to put the K one first, just like you did.
And if we needed the zeros, we know negative 9 is a 0. What's another 0? Negative 9 is a 0. Okay. When is that equal to 0? At positive 5. When is 3x minus 5 equal to 0? 5/3. So we can find the zeros even though they didn't ask us for it. Look at what we've done. We can factor these higher order polynomials. We can determine, and there are no other numbers. You think, well, maybe there are some more numbers you could plug in to make that messy thing equal 0. No. The number of zeros cannot exceed that big exponent. You found 3 of them, that's it. Any questions there? So the problem becomes, suppose they give you a function, but they don't give you a 0. Well, how would we have chosen? Suppose they hadn't given us a 0. Here are the only 3 that would work. Well, there are infinitely many rational numbers. How would you decide which ones to try plugging in to see if you get 0? Because you need something that you can plug in to get 0 to get it started, or use synthetic division. There's something called the rational zeros theorem that takes, out of all the rational numbers in the world, infinitely many rational numbers.
You mean fractions and integers.
Right. Integers and fractions. Then how can we narrow it down? What the rational zeros theorem does is it gives you a finite list, usually about 20 numbers that could possibly be zeros. So if you didn't know a 0, you'd apply the rational zeros theorem, and you'd get about 20 possible zeros. And then you'd have to get started, okay? Does the first one do synthetic division? Do you get a 0 at the end? If so, then great.
Fine.
Continue on factoring. If not, go on to the next one. It'd be tedious, but
doable.
It's doable. It would be doable. So I want to write out the rational zeros theorem first. I'm going to write it down here. Okay? The rational zeros theorem.
Now realize rational just means integers. Fractions.
Numbers that can be written one integer over another. So 7 is a rational number because 7 can be written as 7 over 1.
Or 14 over 2.
Yeah.
Or 21 over 3.
Possible rational zeros must be in the form plus or minus, there's the fraction bar, the numerator must be a factor of the constant term. Factor of constant term. That's the last, remember the constant term is the last number. Okay, there's the constant term.
Constant.
Okay, constant. The denominator must be a factor of the leading coefficient.
Lift it up. Factor of constant term over factor of leading coefficient.
So whatever's on top would have to be a factor of 225. Whatever's on bottom has to be a factor of the leading coefficient 3.
Like in this case, the only factors of 3 are what? What are the only two numbers that divide evenly into 3?
1 and 3.
1 and 3.
Mm-hmm. So
1 and 2, number 9.
Let's do number 9.
It's really not as bad as it looks or sounds.
Suppose you needed to factor 2x cubed plus 6x squared plus 9x minus 8.
I'd say into my phone, factor 2x cubed plus 6x squared plus 9x minus 8, and it would give it to me. If this were a dire circumstance and I really needed it done and I wasn't taking a test and being graded on it. But if you were doing it like,
But if you're doing it as a test, then you can't. That is cheating. So
Delmar has a very good policy about cheating, and we have a link to it on the syllabus.
A very detailed that takes into really every possible consideration. Okay, okay, but y'all aren't going to cheat. Okay. Now, do y'all see that if we wanted to factor this, we'd have a problem? What K value do we use? We don't have an idea. I guess we could say, oh, I like 10. Let's see if 10 would do it. But there are infinitely many rational numbers. The rational zeros theorem gives us a finite list. As I said, we'll wind up with about 20 numbers that may possibly be 0. The first thing you need to know is the factors of the constant term. And you don't have to take into account that minus there. This plus minus takes into account all the possible sign changes. You say, well, what times what equals a negative 8? It could be a positive 1 times a negative 8 or a negative 1 times a positive 8. You don't have to take that into account. All you need are the factors of positive 8.
And do the constant term first, because that's going to be the thing on top.
1 times 8.
What else?
What else? What times what will give you 8? 2 times 4, anything else? So there are all the factors of 8. Now we need the factors of the leading coefficient, the factors of 2. The factors of 2. Oh, this is really nice. What am I going to have here? 1 and 2. We have to take every one of these green numbers and put it over every one of these red numbers. You need an organized way of doing it. You can't just say, oh, I took 4 over 1 and then I'll put 2 over 2. You need an organized fashion. Here's how I'm going to do it. I'm going to take all those factors of the constant term 8. We have a plus or minus 1 over, 2 over, 4 over, and 8 over. You put them all over 1. Then we take those same numbers, 1, 2, 4, 8, and put them all over what? 2.
Now realize each fraction is 2 numbers, the positive and negative. Reduce each fraction.
Now we're going to reduce this first fraction. We're getting 2 possible zeros here. 1 over 1 reduces to 1, so positive 1 or negative 1. And I'll tell you right now, positive 1 and negative 1 will always be possible zeros. Okay? So in your list, they'll always be included. Now, what about the next one? 2 divided by 1 reduces to 2. What's this third fraction going to reduce to? 4 over 1 reduces to 4. The next one? 8 divided by 1 is 8. Now, what about this one? 1 divided by 2. What's that going to reduce to?
Just 1 over 2.
Yes, 1/2, 1 over 2. What about this 2 over 2? That reduces to 1. That's a repeat. We already have that one. What about 4 over 2? What does 4 divided by 2 reduce to? 2. Hey, we already have that one. Oh, this is a nice one. What about 8 divided by 2? That's a 4. Look at that. Out of infinitely many rational numbers, there are only 2, 4, 6, 8, 10. Here are the 10 possible numbers that can possibly make that function equal 0.
Does 7 make it 0?
Is it possible you can use 7 and get a remainder of 0 or plug 7 in? No, 7 isn't there. There's no way it's a 0. So if you needed to factor it, I'd start off with the easy one. Positive 1, use synthetic division. If I get a remainder of 0, factor the remaining quadratic, you're finished. If you don't get a remainder of 0, use negative 1. Keep on going through the list, and as soon as you get a remainder of 0, you're able to start trying to factor by trial and error. Suppose you went through the entire thing and you don't get a 0, that means that the thing isn't factorable. Question? Wait a minute. The rational zeros theorem says the top must be factors of the constant term. The bottom must be a factor of the leading coefficient. Okay? Suppose, hey, let's see. Before we're through, I want y'all to tell me, how is this answer going to change? I'm going to change that 6x squared to a 16x squared, and I'm going to change that 9x to a 59x. How will this work change? Finding the possible zero.
You're right.
Nothing changes. The only numbers you're using are that last one and the first one. Those middle terms have no role in determining possible rational zeros.
Make sure you're doing constant first. If you do the 2 and then the 8 and put them like that, that's one of the wrong answers.
Now, we're not going to make you type in all these things. They're giving them to you as multiple choice. But let's see. It looks like C would have been what you select if you got it wrong by flipping the fraction. Now, they don't have the exact same order.
Order doesn't matter.
The order doesn't matter. A, B, C, or D? A. Okay.
Let's do number 11. 9, 10, 11, 12, the same type of problem. The 13's reviewed. Let me see real fast what's 13. Oh, fog and golf. Okay.
Okay.
Hardly seems like we need to review that. We just didn't we? But okay.
Okay, that's a negative 2x to the fourth. I'm going to have to write some more now. Plus 3x cubed plus 5x squared plus 18.
There are some problems where if you miscopy it, you'll get the wrong answer. But here, like if you'd forgotten the negative in front of the 2,
it doesn't matter. That plus minus that we use from the rational zeros theorem takes into account all the sign changes. The first thing we need is the factors of what number? What number do we start with?
2.
No.
Negative 3.
No.
Factor of the top.
Oh.
So
remember, I always use the constant term. That's what goes on top. That's what I start with. I start with the factors of 18. Okay, good. Factors of 18.
Because you want to sort of be doing this. Top over bottom, top, bottom, top. You know, if you had it reversed, oh, well,
Then,
wait.
right, I mean, yes, I agree. I understand what you're saying. They may not understand it, but I understand
They say
it.
it's consistent.
It's consistent, yes. 18, I'll get us started. 1 times 18. And then 2. Does 2 divide in evenly? Yeah, I think so. 2 times 9.
Now let them tell you the last two.
There are 2 more factors. What are they? Factors of 18. 3 times 6. 4 and 5 don't divide evenly. 6, you already have 6 listed, so you've got them all. Now we need the factors of what? The first thing we do are the factors of the constant term. Then we do the factors of the leading coefficient 2. And once again, you don't have to worry about that negative sign there. Just use the positive number. And there are only 2 factors for 2. What are they? 1 and 2. Well, 9 and 11 are so similar. This is just a coincidence that they both start with 2's, I guess. Then we have to go through. You need an organized fashion. I think what they're doing to get the multiple choice responses, they're taking the blue 1, put it over those 2 numbers there. Then the blue 2, put it over those 2. The blue 3, put it over those. And yet, but the order doesn't matter. I think it's more organized if we take all of those blue factors, put them over 1, then take all of those blue factors and put them over 2. Okay, so
like getting all the whole numbers.
So 1, 2, 3, 6, 9, and 18. Put all of those over 1. There. Put them over 1.
None of those will be fractions.
Then we take all of those blue numbers. Take all of those blue numbers and put them over 2, right. And now there'll be some repetition here, so we'll be able to clean this up and get a nicer list. All of that first row, the over 1s, we can just drop the over 1. 1 over 1 is just a 1. 2 over 1 is a 2. 3 over 1 is a 3. 6, 9, and 18. Okay, what else? 1/2. Do we already have 1/2 listed here? No, so we write it down. 2 over 2 is 1. We already have 1 listed, so we can cross that out. 3 over 2, do we have that listed? No, so we add it to our list. What about 6 over 2? That's 3. We already have it, so mark it out. 9 over 2, do we have that listed? No. $18 over 2? Yes, that reduces to 9. Here's our finite list. Out of infinitely many possible zero or rational numbers that could be zeros, we've narrowed it down to 2, 4, 6, 8, 10, 12, 14, 16, 18. There are really only 18 numbers that could be used as a zero to break that function down.
Someone asked, could I plug a negative 7 over 15 in for x and get a 0? No.
What would your answer be? No.
It's not.
Here are the only numbers that could possibly.
What about 5?
What about 5?
Could I plug a 5 in and get 0?
No,
this
it's
is
not.
a huge deal.
These are the only numbers that could possibly possibly be zeros. And as I said,
How many of these would actually give us 0?
the maximum number would be what? 4.
Mm-hmm.
You couldn't have more than 4 of those. You say, well, there are 18 numbers there. Yeah, of those 18 numbers, there are no more than 4 of them could actually be zeros. Here's what we'll do. We've shown you how to find a list of numbers that could possibly be zeros. We've shown you how to factor a polynomial when you know a 0. Okay? We're not going to make you do the whole thing all at once. Okay, here the thing is, find the list of rational zeros, then find one that is a 0 and begin factoring. Okay? We're assuming that if you ever needed to, you would be able to put these pieces together. But the question is, will you have to go all the way through?
Oh, this is as far as you go.
Yeah. Well, you have the tools if you ever needed to. If you ever had this third-degree polynomial and you didn't know a 0 and you needed to factor it, you have the tools. You get the possible list. Start with 1 or negative 1.
I mean, 1, 3, 9, 27.
Let's do number
1
10
and 3.
also.
We have time, Tim. It's 3:45. Y'all want to see what this number 10 done?
Because it
Yes,
seems
I
that,
mean,
okay.
yes, okay.
Here's the function. They want us to find all the numbers that could possibly be zeros. 3x cubed plus 40x squared plus 40x plus 27. Switch to my work. The first thing I will do is find the factors of... Good. Okay, the factors of 27. What numbers divide evenly into 27? Well, there's 1 times 27. What else? 3 times 9. And that's it. Then we need the factors of what number? The factors of 3, the leading coefficient. This is a good one. Oh, this is nice. What are the factors of 3? 1 and 3. So you take the green numbers, put them all over that red 1. Then you take the green numbers and put them all over that red 3. Okay. So you put all of those over 1. Then you take all of those numbers and put them over 3. You already answered that, didn't you? And the first row, that gives us all the integers. This thing right here, those are all integers. 1, 3, 9, and 27. What else have we got? What else do we add to this list? 1/3. We don't have that written down, so we write it down. What about this one? 3 over 3 is 1. We already have 1 listed, so no. What about this one? 9 divided by 3 is 3. We already have it. Oh, this is really nice. 27 divided by 3. There we have it. There are only 10 numbers that could possibly be zeros. So if I needed to factor that, I'd start off with positive 1 using the
I'm going to have to
synthetic
question
division.
your mathematics, Tim.
What?
Is it possible to add positive numbers together and get a 0? Could you add positive numbers to get a 0? No. 3 plus 40 plus 40 plus...
We can knock out every positive number then.
See, every one of these numbers here is positive. Really, if it's gonna factor, it's gonna have to be with negative numbers.
So try -1 and then -3 until you find one that works. And if none of them work, then it's just not factorable. It's prime.
Oh,
A,
which
B,
one
C,
was
or
it?
D. A, B, C, or D. C, I agree. But that's I see they're going 1/1, 1/3. Then 3/1, 3/3. 9/1, 9/3. 27/1, 27/3. I like our method because it gets all the integers right off.
Okay.
Any questions there?
That ends the starting with number 11. It's reviewing fog and golf. No, 13. Fog and golf, because we got to be able to do that the next time.
Yeah.
Okay. On Wednesday, we're going to be assuming y'all remember how to do that fog and golf stuff. Okay. Ready for me to stop the recording? Any questions?